Good morning, everyone. Today we will continue the second part of the first lecture of Introduction to Measure Theory. So let's get into it. We will continue with equivalent definition of sigma-algebras. So sometimes it is useful to work with our definition that A is a sigma algebra of X if and only if the whole space is in the sigma algebra, and for every pair of elements of the sigma algebra, its difference is also in the sigma algebra. And the third property is that for any countable family in the sigma algebra, its countable union is also an element of the sigma algebra. But by the property that we proved before, we can make some equivalent definition. The first two properties are still the same difference, but the third property is that for any countable family in the set, then its countable intersection will also be an element of the set. So this makes a sigma algebra of X. Of course, X should be different from the empty set. So this is equivalent because in the previous video we showed how this property and how to prove this property. The intersections are always in the sigma algebra with this definition, but we can also prove that this implies this. I mean, the procedure is the same. If you have a countable union, a countable family in the sigma algebra, then its complements, the family formed by its complements, will also be in the sigma algebra, because complements are always in the sigma algebra. Then this implies that the intersection is an element of the sigma algebra if we assume this definition of sigma algebras. Then this is equal to this one, and then we take the complement of this union, and the complement of the complement is the same set. So this proves that this property also implies this one. So these two are equivalent definitions. So to summarize, we have that sigma algebras are closed with respect to complements, differences, also unions, either finite or countable, and intersections, both finite and countable. So continuing with this, we need to now define another not property, but another type of element which is of interest. Definition 2. So let's say that we have a set that is different from the empty set and a countable family of subsets of X, and then we will define the lower limit and the upper limit, also called denote as the limit of the supremum and limit of the infimum. So this is with regards to this family. So this is just a definition. No need to prove anything. This is a definition. So the limit of the supremum of this family will be the intersection of the unions. And this will be the union of the intersections. So what's going on here? This is in fact not different from the limit of the supremum and infimum that you're perhaps already familiar with in real analysis, but that was for sets of numbers, if you remember. But this is not for sets of sets, I mean for families. So let's make some visual examples. Let's say that you have some family of sets A1, A2, A3, and so on. So for the first limit, the limit of the supremum, in the first step, you will make the union of all of these sets. So this will be everything. The first element will be everything. And then this will be our... you can call these some sets B. So this will be our B1, B sub 1. So our B sub 2 will be starting from k equal to 2. So you stop considering this set and you only take the elements that follow. So this is the... let's do it by colors. So B sub 3 will be... then you consider only everything that starts from the third element. So this is... so we have our first few elements, and then we need to intersect everything. So of course the intersection of these, let's work with the first three, will be everything that starts from B3, right? So the intersection of B1, B2, and B3 will be B3. By the way, we are showing these sets. So when you take this to the infinity, then perhaps at some point you will start getting some constant, or I don't know, some sets that are always in all of the sets starting from some index. I mean that perhaps some elements are always in every vk starting from k, I don't know, more than some fixed value. So if everything it's here, I mean for every k, it should be for every k. So if everything it's here, then this will be in the limit of the supremum of a k, because you know this is the intersection. So every element in the intersection should be in every v sub k. So this limit of the supremum, it's only it's composed only of the elements that are in every element b sub k, and the elements b sub k are the union of the elements of the family starting from k. So this is how you should analyze the sets. And equivalently for the limit of the infimum, the first step will be to make intersections. So working with the same perhaps something like this: A1, A2, A3, A4, and so on. So B1 now will be the intersection of everything. So the intersection of everything is of course nothing, because you have disjoint sets. Alright, so perhaps this like this. Now V2 will be the intersection of A1, A2, no, I mean of A1, of A2, A3, and everything that follows. In this example will be just this intersection. I mean, supposing that you only have 3 elements for the sake of the argument. So this will be the white part. And then V3 will be the intersection of A3 and everything that follows. In this case, this will be equal to A3 because we have nothing else. This is just an example. Alright, I mean, to get some equivalent result, we can say that A4, and starting from A4, everything is the whole space. Just to make it similar. So starting from A4, everything is the whole space. But then the next step will be to make the union of all of these sets. So ignoring this fourth step, if we have only these 3 first elements, then it will be the union of the empty set with this intersection and with A3, and so the union of all of these will be of course A3. So this will be the limit of the infimum. So yeah, it's kind of interesting. And now we will work some example, but now it's some more formal example. So let's say that we have our space will be the natural numbers, and every AK will be the set such that. Alright, so it is clear that A1 is the whole space, A2 is starting from everything that follows from 2, and so on. So this is something like a decreasing sequence. So what is the limit of the supremum and the limit of the infimum? Well, for the limit of the supremum, you make the intersection of the unions, and here the union of the intersection. So let's complete it here. So what happens here? If you unite everything that is starting from, I mean, let's call this BK, like we did previously. So B1 will be of course the whole space. B2 will be equal to A2. It's kind of clear because you will make the union of everything starting from A2. So everything else that follows from A2 is included in A2, so the union will be A2, and so on. So for this case, B sub k is equal to A sub k. So what happens when you intersect everything? Well, the intersection of these sets, which are decreasing properly, is the empty set. So this is equal to the empty set. Because if you have an element, suppose you have an element on the intersection, then this element will be in some, let's say we have an element in this limit, then this will be in every BK. But then you know that this alpha should be a natural number, So alpha should also be in +1, and by that I mean that alpha should be more or equal than alpha +1, which is a contradiction. So this limit of the supremum is the empty set. Now for the intersections, it's also clear that starting from the first, let's call this now d sub k. So d1 is the empty set because d1 is equal to the limit of the supremum. But what happens when with d2? Well, if you intersect everything starting from the second, it's the same because the sequence is continuously decreasing. So it's once again the empty set and so on. Everything is the empty set. So if you unite all of these empty sets, the result will be the empty set. So for this case, for this decreasing sequence, strictly decreasing sequence, both the limit of the supremum and the limit of the infimum coincide with the empty set. So for cases like this, when these two limits are equal, we say that the limit exists. So here we say that has a limit, which is the empty set. Now we go with a proposition. So let's say we have an empty set and some family. Here we now will prove two important properties. If the family is decreasing, let's start with increasing, i.e. then it has a limit and is a union. The second is that if the family is decreasing, i.e. that this, like the previous example, then it has a limit, which means that the limit of the supremum is equal to the limit of the infimum, and here this is equal to this intersection. So this is exactly what happened in the previous case, right? We had a decreasing sequence, and these two were equal, and in fact, even though this was a union, it was finally just intersections, right? Because everything was equal. I mean, dy was equal to d2 and so on. So it was just the intersection. So this is exactly the second property is exactly what happened with our example. So now let's do it formally. So for the first property, we go by definition of starting. Let's start with the limit of the infimum. So the limit of the infimum is union of intersections. So what happens here? Since here the sequence is increasing, then when you intersect everything that starts from k, these intersections. So perhaps if we make some graph, it will be more easy to prove. So let's draw it. And this is our first and this is the second one, and the third one, because you know that the family is increasing. Just to show the first. So when you intersect everything, what happens when you intersect everything? What is common in everything that starts from k, for instance, if you start with the first a sub 1, then this intersection will be, of course, a sub 1, because a sub 1 is in everything. It's in a sub 1, by definition, a sub 1 is in a sub 1, but also in the second, the third, and in everything. So this is equal to ak, because if you started in some ak, then ak is in everything that follows ak, by the condition that the family is increasing. So this will be the union of all of the elements of the family, which is half of what we wanted to prove. Now we need to show that this is also exactly what happens with the limit of the supremum. So the limit of the supremum was the intersection of the union. So this is like this, and so let me write it again. Now we are making the union of everything that starts from let's say from A1. If you unite everything, then the result is, of course, everything. I mean, let's write it here. So if you unite everything that starts from K1, we can label this as B sub 1, yeah. So this is B sub 1. So if you unite everything, then this is everything. Of course, nothing wrong with that. In the second case, what happens when you unite everything that starts from K2? What is this? Well, if you start from here, then of course A sub 1 is also in A sub 2. So when you unite everything that starts here, it doesn't make any difference if you unite this with A1. I mean, because A1 is already in A2 and in everything, so this is the same. And in fact, everything is the same. So everything is the same, and it is equal to this. So when you make the intersection of everything, and since everything is equal to this set, then you have this. So it's kind of easy to prove, and that shows the other half of what we wanted to show, because these are equal, and then if the limit of the infimum is equal to the supremum, we say that it has a limit, and this limit is the value that is constant. All right. So now we will go with a decreasing sequence. Let's make a graph because it makes everything more easy to understand. So now the family is decreasing. We start here. This is our first term, and then the second, the third, and so on. So what happens when the limit of the infimum? Limit of the infimum is union of intersections. All right. So what happens when you intersect everything? Well, if you intersect everything, let's call this BK. So B1 will be the intersection of everything. All right. What happens with B2? Well, if you start in A2 and then intersect everything here, since these, since A2 is included in A1, then if you intersect A2 with something else, you don't know, and then you intersect this in A2, this is equal to A2. Why? Because A2 was already in A1. So if A2 is in A1, then A1 intersected in A2 is equal to A2. So we can write it here like this. A2 intersected with the intersection of everything that starts from 3, but this is equal to A1 intersected with A2. So this is finally the intersection of everything, right? And the same applies for the rest. You make the same procedure. So finally everything is equal, and when you unite everything, it will be the same. I mean, this will be the intersection of everything. So now what happens with the limit of the supremum? Limit of the supremum is a intersection of unions. Now, what happens when you unite everything? Well, if you unite everything, of course, the result will be A1. This is, let's say, and this is AK. It's kind of obvious, I mean, because everything is included in A1. So the union of everything is A1. Then if you start from A2, everything is in A2, so the union will be A2, and so on. So each step of these unions will be BK, which is equal to AK. So this is equal to the intersection of everything. So since these two limits are equal, we say that the family has a limit, and the limit is this value. So yeah, this is kind of interesting. Now let's go with a corollary. So now we have a set that is different from the empty set, as always. And now we have a family which is countable. Now the collections, or the families, this is important. Have a limit and is equal to the limit of the supremum of AK. And for the intersection, this is equal to the limit of the infimum of AK. So this is it is important. Why? Because now AK is an arbitrary. This is arbitrary. An arbitrary family. So for arbitrary families, we have now a way to compute or to calculate, or at least know what is this limit of the supremum. It is equal to this limit, and the limit of the infimum is equal to this other limit. So why do these? Let's word the proof. Why do these limits exist? Well, first, it is easy to realize that for this family, if you have the union that there are successive, let's call these elements V1 as always, BK. So it is obvious that V1 is a subset of V2 and so on. Because for the first, you unite everything. For the second, everything is starting from A2 and so on. So this is an increasing sequence. Since it is increasing, then its limit exists. And the same for the second. Let's say this is decay. When you start, no, it is the other way around. This sequence is decreasing. This is wrong. This sequence is decreasing. It is decreasing because B1 has everything, and then B2 has everything except A1. So it is decreasing. So yeah, this sequence is decreasing, and this is the sequence that is increasing. Because for the first, you intersect everything, absolutely everything. So this is some small set. And then you intersect everything that starting from A2. So this is a slightly bigger set, and so on. So this is increasing. And it was the first one that was decreasing. So yeah, since they are decreasing and increasing sequences, then those limits are well defined by the proposition that we just proved here. And so we also have a way to know what is that limit. So in the case of increasing limits, it's the union of everything, and for decreasing is the intersection. So in this case, this is decreasing, and this is increasing. So since this limit is decreasing, let's work this case first. This limit will be equal to, since this is decreasing, will be to the intersection. So this is equal to this. But this is the definition of the limit of the supremum. Yeah, this is just definition. And then for the increasing sequence, the previous proposition tells us that the limit of any increasing sequence is equal to its union. So once again, this is just the definition of the limit of the infimum. So this proves the corollary. We have another one, another corollary. Let's say that we have a measurable space, which is X and some sigma algebra of X. And we have some family, some countable family in the sigma algebra. Then the limit of the supremum and the limit of the infimum of this family, which is arbitrary, is an element of the sigma algebra. And why is that? Well, it is kind of obvious, because the limit of the supremum is the intersection of unions, like this. So this intersection is a countable intersection. So it's a countable intersection of elements of the sigma algebra. So we show that countable unions are always in the sigma algebra. So this is an element of the sigma algebra. And then in the other case, we have countable intersection of elements of the sigma algebra. So this is still in the sigma algebra. Similarly, for the limit of the infimum, this is a union of intersections So both of these properties are properties that are closed in the sigma algebra. So yeah, this is still in the sigma algebra. So it's just by definition. Now we have a proposition. Let's say we have some non-empty set, and we have some family. This is an interesting property, but this family is arbitrary, not necessarily countable, and moreover, it's not a family of subset, it's an arbitrary family of sigma algebras of X. Then the intersection of all of these sigma algebras is a sigma algebra of X, right? So this is an important proposition, because this intersection will be the we can say that it is the kind of the minimum sigma algebra that can be defined on X, something along those lines. So quickly, if you have if this set of indices, if this family includes every sigma algebra, then you know that the smallest sigma algebra is the empty and an X. This is the smallest, just by definition. So that intersection will be the sigma algebra. This family, it doesn't tell you that it has every sigma algebra, but it is an arbitrary family. So perhaps you don't have the smallest sigma algebra here, so this intersection is not trivial. So yeah, let's work this proof. How will we prove this? Well, of course, just going by definition. First, let's call this just as sigma to make things quicker. So does X is an element of sigma? Well, of course, because X is an element of every sigma algebra, so it will be an element of these sigma algebras in particular. So yeah. The second property, let's say we have some pair of sets in the set. Thus A minus B is still in this set. Well, if it's here, then for every it holds that it is here, but those are sigma algebra, so it is here. But if this element is in every sigma algebra, then it is in the intersection of everything. Like this, which is equal to sigma. So yeah, now finally, what happens if you have a countable family of elements in the sigma algebra, then which is intersection, then this is family in every sigma algebra, then its union will be in every sigma algebra. Since it is in every sigma algebra, then it is in the intersection. Let's call this just U. Then U is in the intersection of every sigma algebra. And so yeah, countable unions are maintained in this algebra, in this set. So that makes the set a sigma algebra. So yeah. Now, let's suppose that F is a family of subsets of X, any arbitrary. So there exists a minimal sigma algebra of X that contains F. So we will prove this. This is another proposition. So let's do the proof. Let's define this set B of sigma algebras such that, well, is a sigma algebra of X and F is included in this sigma algebra. Well, of course, we know in the previous video we showed that the power set of X is a sigma algebra of X. So the power of X, so F is of course an element of the power of X by definition. So this will be in the set B. So B is different from the empty set. Now, what happens if we define this symbol as sigma of F, and this will be equal to the intersection of every sigma algebra that contains F. So by proposition, this is a sigma algebra because arbitrary intersection of arbitrary sigma algebras is a sigma algebra. So this is a sigma algebra of X. So we now need to show that this is a minimal sigma algebra of X that contains F, minimum in the sense of inclusion, of course. So if, let's say that we have a sigma algebra A prime, sigma algebra of X such that F is included in A prime, and then of course A prime will be an element of V by definition, and since it is an element of V and this is the intersection of every element of V, then it's in A prime. So that shows that this family is minimal and that it exists. So we call this as the sigma algebra of X generated by F. So this is important because we can generate some sigma algebras that are interesting. Suppose we have a topological space here. This is the space and this is its topology. So this is the topological space. Space, I mean, this is a set, right? So the topology, you know that the topology is included in the power set of X by definition. So we can generate a sigma algebra out of this, like this, because by our previous proposition, right? So this is an arbitrary family. So this topology is also an arbitrary family. So this generated will be called the sigma algebra of Borel. And each element here, let's say it's called a Borelian. This is a Borelian. This is a sigma algebra of Borel, and every element of this is a Borelian. So you know that the topology is included in this sigma algebra, so every open set of X will be a Borelian of X, because you know that every element in the topology is an open set. So you also know that sigma algebras are closed by complements, so all of the complements of the open sets, I mean the closed sets, are also in this sigma algebra by the property. So closed sets are also Borelians. So Borelians will be every open and every closed set. So of course, if you have, since this is a sigma algebra, you can also, Borelians are also countable unions of closed sets and countable unions of open sets, because you know that sigma algebras are closed by those operations. And of course, also you could also make countable unions of closed and open sets, and that union will be also a Borelian. So this is everything for today. If you have any questions, you can write it down in the comments below, and I will try my best to answer them. So we will continue with the second lecture another day. So see you around.